So you can start any of the four Maxwell's equations that we wrote up there to prove those two facts, two identities that they satisfy, that the electric field and the magnetic field both satisfy the heat equation, or the wave equation. Sorry. Um, I'll give you a hint. You could start by taking the curl of E on both sides and see what happens. So we can start. Uh, you could start by curling both sides of this equation. And I'll do it here too. So if I were to take the curl of that equation, minus dB over dt, okay.
The gradient is the potential, right? Or not, right?
The gradient,
Yeah, what is this the gradient of?
the electric field.
All right, it's not. Okay, so just the gradient. Of
Yeah,
the
it's
field.
the gradient of the electric field. Yeah. So now there's an identity that says uh, this is equal. The
Is that only a
gradient
special case? Because wouldn't the gradient of the electric field be toward
the
the
gradient.
charge source?
Say that again.
Wouldn't the gradient of the electric field be towards a charge source when it actually exists? I mean, the electric field can have a gradient, right?
No, that's
Oh,
not.
wait, no, it's not a scalar. It's a vector field, right?
This is not the gradient. This is the gradient would be a vector. This is the first one is partial derivatives times dotted with the electric field. So this would be the divergence.
Okay. Oh,
Yeah, and
Oh.
that would be zero.
right, right.
Yeah. So okay. So minus delta E. And this is the same as minus d over dt. You can take the derivative outside of the curl of b. Okay. Now, this guy here is gradients Laplacian of e minus. Now, uh, we know that this guy is zero from the first Maxwell equation, and the second one would get you minus dE squared equals minus d over dt, and from the second identity or the fourth identity, the curl of b is 1 over c squared d over dt. And yeah, so the minus sign goes away, and we get our identity that says this can go out 1 over c squared d over dt of dE over dt is just d squared E over dt squared. This proves that it satisfies the wave equation. Makes sense, man? How we progressing on that? Okay, and I'll go ahead and get the second part started. So this was part A. Part B, we're gonna having a similar start, but instead we're gonna have take the curl of the fourth Maxwell equation. So the fourth equation, let me rewrite it. So that's curl of B is equal to 1 over c squared, oops, ge over dt. Okay, so I'll take the curl of both sides. 1 over c squared ge. Now, since 1 over c squared is a constant, I can pull this and put it outside. Okay, and I'll use the same identity I used before. G. The identity was the gradient of the divergence of B minus the divergence of the gradient there's no dot here, equals
We treat E as the gradient of a potential field. Potential.
yeah, but you don't need the potential to prove these. These are fairly straightforward, coming directly from Maxwell's equations.
Although, but this is different though, because this is 1 over V, well, C is V, so this 1 over V squared dE dt, not D squared dE dt squared.
Right. Right,
So,
of course.
So if we want to get it in that form, when we want this, when we want E to be a gradient, so we could get a gradient squared, like a D squared potential dt squared times 1 over V squared.
No, you don't need that. Because if you start by taking the curl of both sides, you will get the second derivative of E. I gave you a hint. Start taking the curl of both sides of this equation. Yeah. Okay. Okay. So.
Which equation?
The third equation. This equation.
Okay.
Because when you put a curl on a derivative, that gets you the second derivative, as you will see when you start working it out. Because there's one identity in calculus that says, yeah, if you take the curl of a derivative, this is the same thing as the derivative of a curl, which will get you
like a curl of a curl.
No, the cross product between a gradient and a derivative is the same thing as the derivative times the curl.
Okay.
And for this, you have a Maxwell's equation that you can replace it with, and it will get you the second derivative.
Okay.
because the curl of B is just 1 over c squared dE over dt, and you have d over dt outside. So then you have two derivatives of E. So it becomes d squared E over dt squared. You just need to know how to distribute the curl of a curl using the identity. There's an identity. Do you have those identities in calculus? They should be. I mean, I don't know if you went through
Are
them.
they in this book?
Yeah, of course they are.
Where would they be?
Uh,
What do you think?
I don't know. Let me see. Uh, do you have your physics book? I know they're in the physics book.
Yeah.
Let me see. I don't know where they are here. I know where they are in the physics book. He lists them all here. These are Maxwell's equations. Here you go. They're all here. Product rules, triple product, second derivative. So the one I'm using here is this guy right there. Product rule number 8.
Yeah.
Actually, no, sorry. Product rule number 11. I'm using this.
Okay.
So these are the ones very useful, and you're going to be using those in the physics class too.
Yeah. Okay.
Okay, and so this is going to become 1 over c squared d over dt of the curl of E. Now, let's go back to the question. This guy is 0, so he goes away, and I get minus d squared b equals uh, 1 over c squared. You stand on, or
Oh, it's
when you take the curl of both sides, you see you have curl, then you can use identity number 11 to foil it. Okay, and the reason you do that is because the gradient of E is 0. This is one of Maxwell's equations that we wrote up here. So this guy goes away, and you're left with the second one. Okay, and this is nothing but the Laplacian of E. The gradient of the divergence of E is just the Laplacian.
right.
Or I said it backwards. The
Divergence of
the divergence of the gradient is just the Laplacian.
Oh, okay. I thought it was the gradient of the gradient. I thought it was the gradient of the gradient. Oh no, the gradient's a scalar.
Yeah,
Or,
the
no,
gradient
it's a
is
vector,
not a
it's vector.
scalar. The
It's a vector,
divergence
but-
is a scalar. The gradient is a vector.
Right, but
The gradient is the rate of change. So
the gradient is not a vector field. It's just a vector.
right.
Is a vector field like what's I know a vector is a special case of a tensor. Is a tensor like a vector field? Or
A tensor is a matrix.
no, I mean like is it would a vector field be considered a tensor? Or
No, an example of a tensor would be polarization. Polarization is a tensor of the electric field. It's a
Oh.
matrix tensor of the electric field.
Polarization.
Yeah, this will be chapter 4 in this book.
And that's with respect to like space.
Yeah.
Okay.
Okay, so the gradient of E is, so this is d over dt, and then keep going, minus dB over dt. Okay, and now the minus sign goes away, and finally we arrive at the desired result. Laplacian of B equals 1 over c squared d squared B over dt squared. So we proved part B of that the Laplacian of the, or the del squared B is 1 over c squared d squared B over dt squared.